September 1943. Cold morning light across an airfield in eastern England. Major Harold Whitmore stands beside a B-17 bomber, watching ground crews prepare the aircraft for another mission over Germany. He is an engineering officer in the United States Army Air Forces. His job is to keep bombers flying. But today, he faces a problem that no armor can stop and no gunner can fight. The oxygen systems are failing, and men are dying because of it. The numbers tell a grim story. Between June and August of 1943, Allied Bomber Command records 17 separate incidents of crew members losing consciousness at high altitude. 4 aircraft crash because entire crews black out before reaching their targets. 12 men die not from enemy fire, but from breathing systems that stop working when needed most. The cause is not always clear. Sometimes a regulator freezes. Sometimes a cylinder contains contaminated gas. Sometimes a pressure gauge gives false readings. The result is always the same. At 20,000 feet without oxygen, a man has less than 5 minutes before he loses consciousness. After that, he does not wake up. Whitmore reviews the incident reports in his office. Each one describes a different failure. On the 14th of July, a waist gunner on a mission to Hanover suddenly collapses. His crewmates find his oxygen hose disconnected, the regulator valve frozen solid with ice. On the 3rd of August, an entire crew reports dizziness and confusion at 18,000 feet. Post-flight inspection reveals their oxygen cylinders were filled with gas containing excessive moisture and carbon dioxide. On the 29th of August, a navigator dies when his pressure gauge shows a full tank that is actually empty. He trusts the instrument. The instrument lies. The problem is not new, but its scale is growing. As the bombing campaign intensifies, more aircraft fly higher and stay airborne longer. The B-17s and B-24s operate at altitudes where oxygen is not optional. It is survival. Every crew member wears a mask connected by hose to a central supply or personal cylinder. The system must work perfectly for hours at temperatures far below freezing. Any weakness becomes fatal. Whitmore begins his investigation on the 8th of September. He does not start with theory. He starts with wreckage. At a salvage yard near the airfield, he examines oxygen equipment recovered from crashed bombers. He finds regulators with ice crystals blocking the valve seats. He finds hoses brittle from cold, cracking under pressure. He finds cylinders with residue that should not be there. Each piece of failed equipment tells him something about how the system breaks down. He identifies 3 primary failure modes. First, moisture in the oxygen supply freezes at altitude, blocking regulators and valves. Second, contamination in the cylinders introduces carbon dioxide or other gases that do not sustain life. Third, pressure gauges fail to accurately indicate remaining supply, leaving crews without warning before their oxygen runs out. These are not design flaws. They are maintenance and quality control failures. The equipment can work. It is not being properly prepared or tested. On the 15th of September, Whitmore visits a supply depot where oxygen cylinders are filled and distributed. He watches the process. Workers connect cylinders to a central manifold and open valves. Gas flows. Cylinders fill. The workers check pressure and mark each cylinder as ready. Whitmore asks about purity testing. The supervisor tells him they test a sample from each batch. Whitmore asks how often. Once per week, the supervisor says. Whitmore does the math. Hundreds of cylinders filled between tests. If one batch is contaminated, dozens of aircraft receive bad oxygen before anyone notices. He requests permission to implement new procedures. His commanding officer approves. Whitmore has 3 weeks to design a solution before the next major operation. He works 16-hour days. He does not work alone. He brings in chemical engineers, maintenance specialists, and experienced crew chiefs. Together, they build a system. The first element is heat. Whitmore orders the installation of electrically heated jackets around oxygen regulators on all bombers. The heating elements run off the aircraft electrical system and keep the regulator valves above freezing even at extreme altitude. The modification is simple. A coil of resistance wire wrapped around the valve body, insulated and connected to the power bus. It adds less than 2 pounds to each regulator. It eliminates ice blockage. The second element is purity. Whitmore establishes a new testing protocol. Every cylinder must be sampled and analyzed before installation on an aircraft. Not batch testing, individual testing. He sets up testing stations at each airfield with chemical analysis equipment. Technicians draw samples and check for oxygen concentration, moisture content, and contamination. Any cylinder that fails goes back to the supplier. Any batch that shows problems triggers an immediate inspection of the filling equipment. The process takes time. It saves lives. The third element is calibration. Whitmore mandates weekly pressure gauge checks using master gauges traceable to standards. Every gauge on every aircraft gets compared to a known accurate reference. Gauges that drift out of tolerance are replaced immediately. He creates a tracking system. Each gauge has a serial number and a maintenance card. The card shows test dates and results. If a gauge fails, maintenance crews can trace it back to its installation date and check whether any missions flew with faulty readings. Implementing these changes across hundreds of aircraft and dozens of airfields requires organization. Whitmore creates a quality control network. He assigns oxygen specialists to each base. These specialists report directly to him. They conduct inspections, verify procedures, and track failure rates. Every week, Whitmore receives reports from each airfield. He analyzes the data. He looks for patterns. When one base shows higher failure rates, he investigates. Usually the problem is procedural. Someone skipping a step, someone using old equipment. He corrects it. The first test comes on the 12th of October. A maximum effort mission against ball-bearing factories in Schweinfurt. Over 300 bombers take off. The mission profile calls for sustained flight above 20,000 feet for more than 4 hours. Whitmore monitors the operation from the command center. He waits for oxygen failure reports. They do not come. All aircraft return with functioning oxygen systems. 0 hypoxia incidents. The heated regulators work. The tested cylinders work. The calibrated gauges work. But Whitmore does not stop. He continues to refine the system. In November, he adds a requirement for pre-flight oxygen system checks. Before every mission, crew chiefs must verify regulator function, check hose connections, and confirm gauge readings against a master gauge. The check takes 10 minutes. It catches problems before takeoff. In December, he introduces a standardized maintenance manual for oxygen systems. Every airfield uses the same procedures. Every technician follows the same steps. Consistency reduces errors. The results show in the statistics. Between October 1943 and March 1944, oxygen-related casualties dropped by 87% compared to the previous 6 months. Bomber crews fly deeper into Germany and stay at altitude longer. The sustained high-altitude campaign becomes possible because crews can breathe. They can think. They can fight. Whitmore's work extends beyond equipment. He trains maintenance personnel. He writes technical bulletins. He visits airfields and talks to crew chiefs. He listens when they describe problems. He incorporates their observations into updated procedures. The system improves because he treats it as a living process, not a fixed solution. In February 1944, a B-17 returns from a mission over Berlin with battle damage. Flak has punctured the fuselage and damaged the oxygen distribution system. But the crew survives because the heated regulators continue functioning despite the damage, and the pressure gauges accurately show remaining supply, allowing the pilot to descend to a safer altitude before the oxygen runs out. The crew chief reports this to Whitmore. Whitmore adds it to his case files, evidence that the system works under stress. By spring of 1944, Whitmore's oxygen quality control network operates across every 8th Air Force base in England. Similar systems spread to the 15th Air Force in Italy and the 20th Air Force in the Pacific. The procedures become standard. The heated regulators become standard equipment. The testing protocols become doctrine. What began as one officer investigating failures becomes institutional practice. Whitmore does not receive a medal for this work. He does not lead a famous mission or shoot down enemy aircraft. His contribution is invisible. But it is measurable. Thousands of bomber crew members complete their tour because they can breathe at altitude. The strategic bombing campaign that destroys German industrial capacity depends on aircraft that can fly high enough to reduce flak effectiveness. That capability depends on oxygen systems that work. The war ends. Whitmore returns to civilian life. He becomes a consulting engineer. He applies the same principles to industrial safety systems. He never forgets the lesson from 1943. Complex systems fail in predictable ways. Preventing failure requires attention to detail, rigorous testing, and continuous monitoring. It requires treating every component as critical. It requires assuming that anything that can go wrong will go wrong unless you actively prevent it. Years later, aviation safety investigators study Whitmore's oxygen quality control program as a model for systematic failure prevention. His approach becomes a foundation for modern aviation maintenance practices. The idea that every critical component must be individually tested and tracked, that procedures must be standardized and verified, that failure data must be collected and analyzed. These concepts seem obvious now. In 1943, they were not standard practice. Whitmore made them standard. The silent killer that threatened bomber crews in September 1943 was defeated not by better technology, but by better discipline. The oxygen equipment was adequate. The procedures were not. Whitmore fixed the procedures. He built a system that turned an unreliable necessity into a dependable lifeline. The men who flew the missions did not know his name. But they breathed because of his work, and they completed their missions because they could think clearly at 20,000 feet. The bombers that crippled German war production in 1944 flew high and stayed high because Major Harold Whitmore understood that survival depends on details. And he made sure those details were right.